So let's look at complex numbers. First, we'll define what a complex number is, and then we'll look at adding, subtracting, multiplying, conjugates, and solving equations with complex numbers, and then finding real and imaginary parts. Now, I'm not going to, this first bullet point here, the number system, I'm not going to talk about in detail. Essentially, you can look at the integral notes or in your textbook. So that will be talking about the number systems. You've got natural numbers, which is numbers you can count, so positive whole numbers, and then from there on, a bigger number system is like integers, so negative whole numbers and positive whole numbers, including 0. And then from there, you've got rational numbers, so everything that you've seen before, plus fractions. And then we've got real numbers, which are all the numbers that you know up to now. So anything about all the numbers on the number line, so fractions, decimals, irrational numbers like √2 and or e or pi. And now we've got a new kind of number, which is a complex number, which you usually use the letter Z to represent, and it's of the form, it's a number of the form a plus b I, where I is the square root of -1. Now, let's talk about this. So I is the square root of -1, so we can work out, of course, I squared. It's just -1. We can work out I cubed. That's -1 lot. It's this times this, so it's -1 lot of the square root of -1, but that's just I, so that's minus I. And I to the power 4, well, we can just take our -1 and square that. That gives us 1. And then then I to the power 5, we're back down to, so it's I to the power 4 times I, so that's just I. And as you can see, this carries on going forever, so there's a pattern that goes I. So in fact, ignore this for a second. You say it goes I, -1, minus I, 1, I, and so on. -1, minus I, 1. All right, so one more thing. So these A and B's don't have to be whole numbers. These are just any real number. So it could be, for example, pi plus √2i. And by the way, this includes all the numbers you know already. So what about if I just gave you the number 5? How would that be written as a complex number? Well, that would just be 5 plus 0i. What about the number pi? Well, that would just be pi plus 0i. But we also have numbers such as 2 plus 3i, and so on. Okay, so let's start adding and subtracting. Now, adding and subtracting is pretty easy. It works exactly how you'd think it'd work. It's collecting like terms. Add your... Oh, by the way, one thing I didn't state now, we'll revisit later. The real part of a complex number is this part. So in this case, A. And the imaginary part is b, it's the part in front of I. It's not bi, it's just b. We'll look at that later on anyway. So when adding complex number, we just add the real parts and add the imaginary parts. So if I look at this example 1, z equals 3 plus 2i, w equals 1 minus 4i. I'm adding these two together. Z plus w, well, it's 3 plus 1 plus 2 minus 4i. And I'm just going to write out the answer. Z plus w. Well, actually, for now, we'd write out the whole thing. So it's 3 plus 2i plus 1 minus 4i. Of course, collect your like terms, collect your real parts, collect your imaginary parts. So that gives us 4 plus 2 minus 4. So it's minus 2. So instead of plus minus, right? Let's just write minus 2i. Done. Okay, let's look at part 2. It works exactly as you'd expect. Now I'm not going to write out the whole working out. It's pretty simple. Z minus w, well, let's just look at these. 3 minus 1 is 2. In fact, it's really useful writing it like this. So z minus w, 3 minus 1 is 2. 2 minus 4 is plus 6. So it's 2 plus 6i. And also notice this is not a z, it's a 2. Whenever I write a z, I'll put a line through it just so that you can tell the difference between z and a 2. And part 3, w minus z, well, it's 1 minus 3, which is, so w minus z is 1 take away 3 is minus 2. Minus 4 minus 2 is minus 6. Done. Adding, subtracting, very easy. Okay, let's move on to multiplying. Okay, so multiplying, it works as you just multiply out like you'd expect. So multiply out your brackets, and the only thing you have to remember is I squared is equal to -1. It's pretty easy. So let's look at the first one. So try these on your own. Actually, if you're confident, try these on your own, and then pause, try them on your own, and then check to see you got them right. So 3 plus 4i times 2 plus i, 3 times 2 equals 6, 3 times 2i equals 3i. So it's the same way of multiplying that we've learned from primary school. 4i times 2 is 8i, and then 4i times I is plus 4i. squared. Now we need to remember I squared is a -1, so this is in fact a -4. So let's simplify all this. So 6 minus 4, which is 2, and then 3i plus 8i is 11. Done. Let's look at the second example. So we've got 4 minus I times 3 plus 2i. Now, I'm still not going to skip yet. In the last one, I think I'll skip a few steps. So that's 4 times 3 is 12. And then we've got minus 3i plus 8i. So it doesn't matter how. Plus 8i minus 3i. And then we've got a minus 2i squared. Now, I squared is a -1. So it's minus 2 times -1. So this is a plus 2. So this whole thing gives me 14. And 8i minus 3i is plus 5i. Okay, part 3. Now we've got 2 plus 3i times 2 minus 3i. Now we can do it as we've done before, but instead let's be a little bit smarter and see, well, notice this is the difference of two squares. When we do the difference of two squares, all we need to do is square this and square that and put a minus in the middle, and we're done. So this is 4 minus 9i squared, and this is in fact I squared is a -1. This is 4 plus 9, which is 13. Done. Now this is actually always true. This is the conjugate of this complex number. We'll look at that soon. When you multiply a complex number by its conjugate, you just get a real number. Okay. As we just said, a complex number. So let's look at that. So the complex, let's say if z is equal to a plus bi, its conjugate, which you'll write as z star, is equal to a minus bi. All you do, you change the plus to a minus. If it was a minus, you change to a plus. That's what's in the middle. What's in front of the a doesn't matter. The a could be negative, positive, doesn't matter. Now, in FP1, we don't use conjugates that much in terms of other than testing that you know what they are. If you do FP2, if you do complex numbers later on, conjugates are actually very, very useful. So let's work out these examples. It's conjugate of if minus 2 plus 3i. Well, the conjugate of this, I just put the answer, write down the answer, is minus 2 minus 3i. Notice these aren't equal. If this is z, then this is z star, its conjugate. Let's look at part B. Well, the conjugate of this is simply 8 plus 9i. And for C, the conjugate of that is 2 minus root 3i. Let's look at something a little bit trickier. So let's look at D. Let's imagine they wanted you to work out the conjugate of Z minus 2i. So now when doing something like this, remember Z is just any complex number. So I'll represent Z with A plus BI. It's any complex number. So I'm actually working out the conjugate of this. Now when doing this, you could, if you want to, just change the sign here and change the sign there. I think it's better in general to actually gather your terms. So in fact, I'm working out the conjugate of A plus B minus 2 lots of I. And to work out the conjugate of this, now is a simple case of just to change the sign there. So that the conjugate of this is equal to A minus B minus 2I. Now you could multiply this out if you want to. You say it's minus bi plus 2i, but it's actually better to write it in this form. Okay, done with conjugates. Equations with complex roots. Now let's look at this quadratic equation. Now you've got various methods. You've got factorizing. Now this one I don't think factorizes. If it doesn't factorize, you've got completing the square quadratic formula. In this case, you can use either method. Let's complete the square on this. So what do we get? And I'll do it with quadratic formula as well, but they are actually the same. That's how you complete the square on a general on ax squared plus bx plus c, and you get the quadratic formula. So x plus 3 squared minus 9. This is the same as x squared plus 6x plus 13 equals 0. Let's rearrange it. Remember, we're trying to solve. We're trying to find x. So that gives us 4, take it over, so minus 4. Now when I do the square root, so x plus 3 is equal to the square root of minus 4. Remember, plus or minus when you're doing this, when you're solving an equation like this. We'll leave this alone for now, though before you said, oh, I can't do this, but we can do this now. We'll leave that. So it's x is equal to minus 3 plus or minus the square root of minus 4. Now this we could write as minus 3 plus or minus root 4 root minus 1 using our rules of indices or roots. So what's that equal to? Well, that's minus 3. Square root of 4 is 2, plus or minus 2, this is I. Done. Now you can, if you're comfortable, you can do the whole, let's just see for once doing this with the quadratic formula. It's a little bit less interesting doing it this way, but I think some of you are more comfortable with this. So x equals minus b plus or minus square root of b squared minus 4ac over 2a. So let's just plug everything in. So minus b, so it's minus 6. Again, I'm bored, but just by saying this or doing it, I mean, there's no point doing this if you can do this, in this example anyway. B squared, in fact, you're more likely to make a mistake doing this. So b squared is 36 minus 4, lots of AC. A is 1, C is 13. So it's 4 times 13 is 26, 52. Over 2, lots of A is 1, so it's over 2. And so that's minus 6 plus or minus the square root of 36 minus 52. That's a 16, that's minus 16 over 2. And then this, you can already see, this will give us that in the end. So this is minus 6 plus or minus square root of 16, square root of minus 1. Again, you don't need to write out every single step. This is equal to, and let's just simplify all of this. So this gives me a 4 divided by 2, minus 6 divided by 2, so it's minus 3, plus or minus, so that's 4 divided by 2 is 2, and that's an I. And done. Again, this has more steps, but in fact, I think this is probably, once you know how to do this stuff, it's easier. And I would say, if your coefficient, if this is an even number, if your b is an even number and your coefficient of x is 1, complete the square is easier. If, on the other hand, you had a 2x squared and you had a 5x, then quadratic formula will probably be a little bit easier to do. Okay, example number 4. Find a quadratic. By the way, these are my two solutions. I've got a quadratic, I've solved it. Example number 4. Find the quadratic equation which is roots x equals 4 plus 2i and x equals 4 minus 2i. So there are two ways of doing this. So one way is just using brackets and multiplying it out. The other way is using sum of the roots and product roots. So let's do it let's say the Dala way, or less interesting way of doing it. So these are my roots. So I can write this as x minus 4 plus 2i and x plus, x. So put a bracket around the 4 plus 2i, and it's x minus 4 minus 2i. Okay, so we just need to multiply these out and simplify. One thing, let's just check. I'm looking at these. This is x minus 4 plus 2i. So it'd be x minus 4 plus 2i. Just minus 4. All right, so a quick check. You can't use completing this. You can't use the difference of two squares because this would be minus 4 minus 2i. It's still minus 4 plus 2i. You can't do this. So we just need to multiply this out. So what does this give us? So we get x squared minus x times 4 minus 2i minus x times 4 plus 2i plus 4 plus 2i 4 minus 2i. Now this one we can use the difference of two squares. Let's just simplify this. So x squared minus 4x plus 2. In fact, instead of doing that, let's simplify it. Let's just start looking at this and think about what counts. So I've got a minus 4x here. I've got another minus 4x here. So I have minus 8x. I've got a plus 2xi. Then I've got a minus 2xi. So those will cancel out. So let's not bother with that. And then this we multiply out using difference of two squares. So it's 16 minus 4i squared. So it's 16 plus 4, which is plus 20. So it's not so bad. All right, the other way you can do this is using the sum of the roots and the product of the roots. So remember, these are my two roots. Imagine think of that as an alpha, that's beta. So what's my sum of my roots? Alpha plus beta is equal to 8. Well, that's it. 2 i's cancel. Alpha, beta, product of the roots. So this requires a little bit of working out. It's not that bad though. So it's 4 plus 2i times. And by the way, remember this is your minus b of array. And 4 plus 2i times 4 minus 2i. And we already know what this is. This was 4 times 4 is 16. And then it's a minus 4i squared, which is actually a plus 4. So this is 20. And this is your c over a. And then let's say let a equal 1. Then my b is equal to minus 8. And my c is equal to 20. And then this gives me x squared minus 8x plus 20. Remembering actually one thing I didn't do, we have to make this equal to 0. We have to make that equal to 0, otherwise it's not a quadratic equation. Same thing here. Done. So in terms of writing, you have to actually write more for this, but I think this is probably the faster way of doing it. And you're less likely to make mistakes. There are lots of things you have to multiply out here. Here you just had to multiply out one thing, and then you do have to, of course, use your roots knowledge. Okay, example number 5, equating real and imaginary parts. Now, as I said before, let's say if z is a complex number, which is a plus bi, then the real part of z, which we'll write like this, is equal to a, and the imaginary part of z is equal to b. Now, if two complex numbers, so on this side, if you look at this equation, we've got left-hand side and right-hand side. This is a complex number, and when we work out this side, we'll get a complex number as well. For two complex numbers to be equal, the real and imaginary parts have to be exactly the same. So we're going to use that fact, and we're going to compare real and imaginary parts. And we're going to have, sometimes some of these times we'll have simultaneous equations, other times we have something rather simple, and we're going to use that. So if essentially, notice the imaginary part of this complex number is not bi, it's just b. So remember, if two complex numbers are equal, their real and imaginary parts must be equal, and both of them must be equal. So, example 5. We're going to solve the equation 3z minus 2z star. Now, remember, this is the conjugate of z equals 4 minus 15i. So, for this, we're going to say, let z be equal to, well, a plus bi. I think sometimes in the notes, they start using x plus iy. Doesn't matter which one you use. Of course, if that's z, then z star, or z, the conjugate of z, is a minus bi. Let's plug this into my left-hand side. So I'm going to work it out straight away. So I've got 3 lots of this. So I've got 3a plus 3bi. Then I've got minus 2 lots of this. So I've got minus 2a, and then minus 2 times this. So it's plus 2bi. And that's equal to 4 minus 15i. Let's gather terms here. So let's gather my real parts and imaginary parts, so the bits with the i's and the bits without the i's. So I've got 3a minus 2a, so that's just a. And I've got 3bi plus 2bi, so that's 5bi. So I've got a plus 5bi, and that's equal to 4 minus 15i. So let's compare real and imaginary parts. So I'm just going to take real parts here. So what's my real part here? Well, it's a, isn't it? What's my real part here? 4. What did I say before? Two complex numbers are equal. The real parts must be equal, and so must be the imaginary part. So from this, we can just say a is equal to 4. All right, let's compare imaginary parts. It's a little bit more work, but not much more. What's my imaginary part here? Well, my imaginary part is this bit. You're not including the I, just that bit, the bit in front of the I. Here, it's all of this. Now, of course, we include the sign. It's minus 15. So what do I have? I've got 5b equals minus 15. So, of course, that gives me b is equal to minus 15 divided by 5. So that's minus 3. So let's finally solve. So what do we have to do? We want to solve this equation. Solving this equation means finding what z is. Well, we found a, we found b. We said z equals a plus bi. So finally, z is equal to 4 minus 3i. Okay. Example number 6. So we've got 2 left. So solve the equation. This is going to be exactly the same. So maybe pause now, try this one on your own. It's nothing different here, nothing actually especially interesting. Well, I think this one may be one where we need to use simultaneous equations, but let's just start off by saying z is equal to a plus bi, plug it in, multiply it out. So we've got 3 minus 2i, a plus bi minus 1 plus 4i equals 7 plus 4i. Now I don't want to multiply this by all these 4 things. So what I'm going to do here to make my life a little bit easier is to gather my terms, to gather my real parts together and imaginary. So this is the 3, although you don't need to do this step if you don't want to. So I've got a minus 1. So I'm just going to think about that as one object. And I've got a 4 plus b. So plus, say, 4 plus b or b plus 4, doesn't matter. And that's equal to 7 plus 4i. So now let's multiply these out. Multiplying out now is a little bit easier. So we do 3 times this. So we've got 3 lots of a minus 1, 3 lots of this, so plus 3 lots of 4 plus b I, and then I've got minus 2i lots of this, so minus 2i lots of a minus 1. Again, it's not that much easier. It's still a decent amount of work. Nothing. So as long as you're careful, though, you shouldn't get any of this wrong. It's not difficult. It's just time consuming. So we've got minus 2 lots of 4 plus b. Of course, then we've got an I and an I, so it's an I squared. So do write this in as long as well. You either write this in or you change the sign. I think it's better to write it down, and then you'll know that you actually have, then you'll know, okay, now I need to make this positive because I squared equals minus 1. Still equal to 7 plus 4i, by the way. Okay, so let's expand and simplify. So we've got 3a minus 3 plus 12i. In fact, I'm gonna, okay, equals plus 12i plus, in fact, actually, we want to compare real and imaginary parts. So let's gather my i's together. So my i's, these are my i's. This is everything that's got an I in it. So I'm going to factorize out the I from this. And these two, let's put these, before that, let's actually combine my real parts. So we've got 3a minus 3, and then this, of course, this is, I squared is a minus 1, so this is plus 2, so it's plus 8, plus 2b. So this is my real part. So this will be equal to 7. We can actually simplify this, so, but before that, let's actually write down what the rest of this. Let's finish this off. So I'm just gonna factorize out the I from this. It shouldn't be equal, sorry. And so let's just write it as I, and let's put a plus there. And what do I have in here? I've got 3 lots of 4 plus b, and in fact, let's just multiply it out now. So I've got 12 plus 3b. And in here, I factorize out the I, so I've got minus 2a, and then minus 2 times minus 1 is just plus 2. And this whole thing is equal to 7 plus 4i. Now, I did it like this. You may think, why did I bother doing it this way? Because now I can compare my real and imaginary parts. So I gathered all my things with the i's together. So my imaginary part is this. And this whole thing must be equal to my imaginary part here, which is 4. And my real part is all of this. And this is equal to 7. So we're not done yet. We still need to, we'll actually have some simultaneous equations. So let's simplify these. So what is this? My first equation? This one gives me 3a plus 2b plus 5 is equal to 7. So 3a plus 2b plus 5 is equal to 7. And actually, we're going to simplify that. Let's just leave it like that for now. And then this one gives me 12 plus 2, so it's 14. Minus 2a plus 3b, and that's equal to 4. So let's not leave it like this. So what I'm going to do is get from each of these, don't want numbers here as well, so I'm going to move this, subtract 5 from both sides, subtract 3 from both sides. So this gives me 3a plus 2b is equal to 7 minus 5, which is 2, and this is minus 2a plus minus 2a plus 3b. I forgot the b here. There's a b there. So plus 3b equals 4 take away 14, which is minus 10. Now we've got simultaneous equations. We solve these simultaneous equations and we'll get our answer. Alright, so I'm going to skip ahead a little bit. I'm not going to do the whole simultaneous equations. It's something you should be comfortable with. You should have done this plenty of times. So let's just check. So 3x plus, if you look at your notes and integral, they actually do the working out. So I'm just checking my numbers. So 3a plus 2b equals 2, minus 2a plus 3b equals minus 10. These are all correct. You do simultaneous equations. This gives us a is equal to 2, and we'll get b is equal to minus 2. So finally, my z is equal to 2 minus 2i. Okay, so this bit is just simultaneous equations, exactly the same as you did in GCSE. So make either your a's the same or b's the same, eliminate, work out, and then substitute that in, find out your a, and then substitute in to find your b. I'm not going to do this. Something you should find pretty simple. Okay, finally, last example. Example 7. Find the real numbers a and b with a greater than 0 such that a plus bi squared equals 16 minus 30i. So this looks a little bit different, but we're still going to use the same techniques we've used before. So pause now, have a go at this, or just think about how you do this. Okay, well, if you don't know what you're going to do, well, I don't see exactly the entire root, but we've got a square here. Maybe we should just try multiplying out the square. So again, just because you can't see exactly the whole root doesn't mean you can't do anything. So I'm pretty sure what we're going to do right now is right. But even if I didn't know, do something. Doing something is better than doing nothing and just sitting there. So let's multiply this side out. So what do I have? So I've got a plus bi squared. Of course, that means it's a plus bi. A plus bi. And that's just a squared plus 2abi plus b squared I squared. But of course, I squared is a minus 1. Let's just write it for now. So b squared I squared. This simplifies to, this is a minus b. So b squared. So this is a squared minus b squared. I squared is minus 1. So it's a squared minus b squared. Notice I write the I part at the end, just to keep it of the form something plus something I. And then it's plus 2abi. And that's equal to 16 minus 30i. All right, so let's compare real and imaginary parts. So my real part is this, My imaginary part, this, and this. Okay, so my imaginary, so let's just use some nice colors. So that's so 2ab and minus 30. So, sorry, apologies, my pen stopped working for some reason. So minus 30. So let's start with, so we've got a squared minus b squared is equal to 16. And we've got 2ab is equal to minus 30. Solve the simultaneous equation by substitution. So this equation rearranges to give me b is equal to minus 30 over 2a. And let's just simplify that a little bit. So that's minus 15 over a. Let's sub that into this equation. So what do we have? We've got a squared minus b squared, but b is minus 15 over a. So we've got a squared minus 15 over a squared equals 16. All right, now we just need to multiply these things out and then solve. So this is a squared minus 225 over a squared equals 16. Multiply through by a squared gives me a to the power 4 minus 225 equals 16a squared. bring everything over to the same side, make it equal to 0, gives me a squared, so a to the power 4 minus 16a squared minus 225 is equal to 0. Now this is a quadratic in a squared. So at this stage we can use the quadratic formula, we can complete the square. Remembering now this is while it looks like a quartic equation, this is a quadratic in a squared. So I think this one will factorize. So let's think about, can we think of numbers that multiply to give you 225 and add to give me 16? And I think so it'll be a squared equals 0. Numbers to multiply, so it's obviously it's not going to be 15 and 15, 25 and 9. Yeah, 25 and 9, doing that, give me that. Now I just need to think about this. It's minus 25 plus 9. Let's just check. So 25 times 9 is 225. And you get minus 16. So that, what do we get? We get a squared is equal to 25, or a squared equals minus 9. But we were told that a is greater than 0, and a is a real number. Real numbers a and b. This one will give me a is equal to plus or minus 3i. So we're going to ignore this because we've been told a is a real number. So what does this give me? This gives me two possible values. This says a is equal to plus 5 plus or minus 5. But we also told a is greater than 0. So for a is greater than 0, so we actually know a is equal to positive 5. Now, so let's work out b. So b was equal to minus 15 over a. So b is equal to minus 15 divided by 5, which is minus 3. So our final answer, as said, is equal to 5 minus 3i. Alright, so that's it. So this last one was a little bit trickier. It required a lot of work, but the same technique in general. I guess solving this quartic equation was a little bit trickier. Again, you're not going to be expected to solve a quartic equation that you can't use some kind of trick. So it'll be some kind of quadratic, or there'll be something you can do to it. You are not expected to, at this stage, to be able to solve any quartic equation. Same thing actually, cubic to some extent as well. You don't need to know the factor theorem or the remainder theorem for Fp1. Okay, so that's it. So go away, have it, and try some exam questions. That's it for now.